Quality Control and Improvement, Module 3, Lecture 2, Statistical Inference, Hypothesis Testing. Learning objectives for Lecture 2 are to test hypotheses on a single variable. Reading assignment is Chapter 4, pages 117 to 126. And again, this particular chapter, Chapter 4, is pretty theoretical. And as we'll see in the next chapters, these concepts get pulled over into the next chapters and dealt with control charts, but it's much more experimental and much more user-friendly, I think, than actually understanding how hypothesis works. But it's good to have a basic understanding of how to test hypotheses, so we can understand how a control chart works. So let's proceed forward. So what is hypothesis testing? A key goal in many engineering quality control applications is to check whether the data gathered supports certain statements or predictions. A statistical hypothesis is a conjecture about a population parameter. This conjecture may or may not be true. For example, the mean income for a resident of Denver is equal to the mean income for a resident of Seattle. So in this case, the population parameter is the mean income. One population consists of the residents of Denver and the other consists of the residents of Seattle, and our job here in this case would be to compare the mean incomes of those two cities. There are two competing types of statistical hypotheses. One is known as the null hypothesis, represented by H0. This states that there's no difference between a parameter and a specific value. There's no difference between two parameters. The alternative is that there is a difference. And we'll see how this applies in a couple of examples. So in hypothesis testing, you basically have three different areas. Let's take a look, for example, at comparing the mean of a population. So let's say we are interested in determining how the mean falls with reference to this value k. So k is what we've sampled. This is our sample mean, for example. And we're basically interested in there's three ways you could do this. A two-tailed test says the hypothesis, the mean is actually equal to k. So the two tails would be that it's equal to k, but not equal to k means that the mean could fall over on this side or could fall on that side. A right tail test would simply fall on the right side, mu be greater than k. The left-hand test would say that mu would be less than k. So let's take a look at an example that I think will clarify this idea. So state the null hypothesis and the alternate hypothesis for each case. A researcher thinks that if expectant mothers use vitamins, the birth weight of babies will increase. The average birth weight of the population is 8.6 pounds. So here, if you think about it, the mean is actually 8.6, right? So what we're asking is the hypothesis is that H0 is equal to 8.6. Now, what's the alternate hypothesis? The alternate hypothesis would be the birth weight will increase. So that would mean the alternate hypothesis would mean the weight is greater than 8.6. So when you look at this, so here you can determine the null hypothesis or the alternate case. So when we make a conclusion from a statistical test, there are two types of errors that we could make. These are called type 1 and type 2 errors and are defined as follows. A type 1 error occurs if we reject the null hypothesis when in actuality the null hypothesis is true. A type 2 error results when we do not reject the null hypothesis when the null hypothesis is actually false. So you can lay this out in a little grid here. So for example, if let's say reject H0 and H0 is true, well that's a type 1 error. If you reject H0 and H0 turns out to be false, well then that's a good job. That's actually the correct decision. So what if we do not reject H0 and H0 is true? Well then that's the correct decision. But if you do not reject H0 and H0 turns out to actually be indeed false, well then that's what's known as a type 2 error. One important point here though is when the null hypothesis is not rejected, we do not accept it as true. There's nearly not enough evidence to say it is false. This is, if you consider the jury trial analogy, this may become a little bit more clear. we don't find people innocent. We only find them guilty or not guilty. So if someone is found not guilty, it does not mean that they were proved innocent. It only means that there was not enough evidence to reach a guilty verdict. So we conclude the alternate hypothesis when we reject the null because the data clearly support that conclusion. Another term that we often hear when dealing with tests of hypotheses is what's referred to as the level of significance. The level of significance is defined as the probability of rejecting a null hypothesis by the test when it is really true. This is denoted by the symbol alpha, the level of significance. So in other words, P for type 1 error is equal to alpha. The confidence level refers to the possibility of a parameter that lies within the specified range of values and is given by 1 minus alpha. So for example, the level of significance of 0.05 is related to the 95% confidence level. Another way to look at this is that for a left-sided test, the rejection region is to the left side, the shaded region here. For a right side test, the rejection region is shaded in the right side, and the rest of this would be clear. And in a two-sided test, the rejection region is both shaded regions, and the white part is the non-rejection region. Another way to test for hypothesis is what's known as p-values, and this is the method that I prefer because it's a little bit easier. The traditional ways to report the results is to state that the null hypothesis either was or was not rejected at a specified level of confidence. In my opinion, again, the better approach is calculate the p-value. The p-value is the smallest level of significance that would lead to rejection of the null hypothesis. And Minitab will calculate this for us. The p-value provides a measure of the credibility of the null hypothesis. It measures the weight of evidence against the null hypothesis. Specifically, it's the risk that you have made an incorrect decision if you reject the null hypothesis. The following table is useful for the 95% confidence level. So if the p-value is less than 0.05, this indicates that the null hypothesis is very unlikely, and we should reject the null hypothesis. If the p-value is greater than 0.05, this indicates that the null hypothesis is very likely true, and it should be accepted, or it fails to reject. So let's take a look at an example and see how you apply this. So it's been reported that the average credit card debt for college seniors is $3,262. The student senate at a large university feels that their seniors have a debt much less than this. So it conducts a study of 50 randomly selected seniors and finds that the average debt is $2,995. And the population standard deviation is $1,100. So let's conduct this test based on a type 1 error of alpha equals 0.05. So this would be at the 95% level. So the first thing we need to do is state the hypothesis and identify the claim. So the null hypothesis is that the mean value is $3,262. The alternate hypothesis that we claim is that the mean is less than $3,262. This is what the Senate's trying to prove. So for Minitab, go to Stat, Basic Statistics, 1 sample Z, and enter the data from the problem as shown. Our sample size is 50, our sample mean is 2,995, and our known standard deviation, 1,100. Our hypothesized mean is 3,262, and click the little symbol to do the perform hypothesis test. If you click on options, you can enter the confidence level, and this is where we enter our 95%, and the alternative hypothesis is that the mean is less than the hypothesized mean. That's what we're trying to show. So let's compare the results and make a decision to reject or not reject the null hypothesis. So when you hit OK in the data in Minitab, Minitab will print out the statistics, the number of samples, the mean. It'll go to the 95% upper bound for the mean. It'll put the null hypothesis and it'll list the alternate hypothesis, And it also gives the p-value. And here in this case, notice it's 0.043, which is less than 0.05. So that indicates the null hypothesis is very likely unlikely. In other words, we should accept the alternative. So to summarize, since the p-value is less than 0.05, we have evidence to support the student senate claim that their university seniors have credit card debt that is less than the reported average debt. This is based on the type 1 error of 0.05, which means that we falsely make the claim above about 5% of the time.